You get to think deep. Think deep about some wild stuff. But we're not there yet. We're still in PFD, very practical, very procedural, not much deep thinking. All you have to do is recognize whether it's linear or quadratic. So we'll do that first. Maybe that'll help wake us up before we do the abstract, crazy math stuff. This is where we were. We were doing our first example that had a couple of irreducible quadratic factors. So we want to remember that we're looking at the denominator, we're factoring the denominator. The fundamental theorem of algebra says every polynomial with rational coefficients can be factored into linears or quadratics. And the quadratics are irreducible if they're not factorable. So sums of squares are classic irreducible quadratics. If we see a quadratic and we don't know if it's irreducible or not, we look at the discriminant, b squared minus 4ac. And if that's negative, it's irreducible. That means you have to have imaginary zeros if that discriminant is negative. Okay? So, we've got these two obviously irreducible quadratics because they're sums of squares. Y squared plus 1 squared, y squared plus square root of 2 squared. Okay, so those are sums of squares. And we got down, we did our regular PFD equation, we did our system, and we got here. This is where we're at. So we're going to break it into two integrals. The first one's an immediate arctangent. It's the standard basic arctan. So let's go ahead and just integrate that one right out of the gate. So that's inverse tangent of y. And then the second one, again, I will do this with a little bit of algebra first. I'm going to factor that 2 out and put it in that basic form so that we only have to remember one formula for integration. So I'm factoring out the 2, and that's what happens when we factor out the 2. Everybody agree with that? Hopefully this is transparent by now, but if you don't see it instantly, then you do this. You put a 2 over 2. That's the 2 that's being factored out in the denominator. It leaves us with that. And then we want to write that as a single square. Single square. So we will have arctangent of y minus 1/2. And this one, a little trickier because that's not it's not a perfect square integer. So we have to write it as y divided by square root of 2. There. Now we've rewritten that into our basic arctan form where we have the 1. We have a sum of squares with a trailing 1. Now we can integrate it using reverse chain rule. So our final step is, well, maybe we have a simplification step. Let's see. Actually, I think I can get away without having to write a whole nother line. Let's see. So we have that. Arctangent of whatever's in the parentheses with the variable. But then we have the RCR, reverse chain rule. Reverse chain rule says that if you were going to do substitution and it's linear, when we integrate, we take the derivative of that quantity in the parentheses, take its derivative, and then divide by that quantity's derivative. And what is the derivative of that right there? So we can think of this as 1 over square root of 2 times y. So it's just linear. The derivative is just a coefficient then. So the derivative is 1 divided by root 2. And we have to divide this by 1 over root 2. Dividing by 1 over root 2 means multiplying by root 2 over 1. So that tells us this right here is going to become a root 2 from the RCR. So that is from reverse chain rule. And then we have our plus c. So So there is our final answer with this irreducible quadratic linear factors. So the one thing that we are noticing is that when we have an irreducible quadratic, we put a general linear as the numerator. So if you have a linear factor, you put a constant up top. If you have a quadratic factor, you put a linear up top. You subtract one from the power. And let's do another example. So here's an application one. The application part's not so complicated. We're just trying to find the area under the curve. We see two factors here. Those two factors, one of which is linear, the other is an irreducible quadratic. All right. That's a curve that you would never be expected to graph. I would give that graph to you if it was on a test. That's a little weird. Okay, well, we're just integrating from 0 to 1. That's all we're doing. So let's at least write that down. We're integrating 0 to 1, this function over here, and they factored the denominator for us. So if we can factor the denominator, PFD is a great option. We've seen a bunch where the denominator was not factorable, and so we did a completing the square technique, tried some other things. If the denominator is factorable, PFD is the sort of standard approach, if the denominator is factorable. So we have one linear and one irreducible quadratic. So we're going to take that rational expression there, and we want to break it into partial fractions. So we're trying to undo this rational function. We're trying to break it apart into partial fractions. The linear one creates a partial fraction of a constant over x plus 1. Anytime we have a linear factor, we'll go with a constant up top. And then our irreducible quadratic will have a linear up top. So we'll just move through the alphabet, grab the next two letters, B and C. Yeah?
Why would it be positive and not negative? Because it's negative x.
So that we're completely ignoring this numerator at the moment. So this structure that we create is only based on the denominator. What we will see is that one of these A, B's, and C's will be negative in order to create that negative. Like we need to solve for A, B, and C in a way that will generate that minus there. So that's going to come out in the wash. When we create our structure here, the only place we look is the denominator. Take the linear denominator, put a constant up top, take the irreducible quadratic, put a linear up top. So it's all based on the denominator. The numerator is where we're going to go to next, but we're not there yet. So that structure is purely from the denominator. Let me ask a related question. If this had a square on it, on the linear, what else would be on the right-hand side? What else, if there was that square on that linear?
D over x plus 1 squared.
D, a constant, because this is still a linear factor. Even though it has multiplicity of 2, it's still linear. The factor is linear, it's just repeated. So it has a multiplicity. So we would still go with constant here, but then we would have to have the denominator be to the 2. Because we have a partial fraction for every power of every factor. And if there happened to be, say, a 2 on this one, we would have to put another ex plus f over that quadratic squared. So So we have to have a partial fraction for every power of every factor. Anytime the factor is linear, constant up top. Anytime the factor is quadratic, a linear up top. Okay, so we don't have those, and we're glad we don't have those because that would be quite a lot of work. So now we have this as our structure for our PFD. The next thing we do is create what I call the PFD equation. The PFD equation we find by clearing out the fractions. So we multiply both sides of the equation by the left-hand side denominator. So we're going to multiply the entire equation by the denominator on the left. And that creates our PFD equation. So our PFD equation, we get that on the left. When this double factor here, we have two factors, this double factor comes and hits this fraction, the x plus 1's cancel. So we're going to have a multiplied by x squared plus 1. When that double factor comes here and multiplies by that fraction, the x squared plus 1's cancel. So we'll have plus bx plus c multiplied by x plus 1. So there's our PFD equation. And here's where we have to make choices. Here's where we say, we're going to go with the traditional method and just multiply everything out and set up the corresponding coefficients so that you build your system of equations. Or you could say, hey, I see that there's a convenient value, so I want to do like a hybrid approach. We can't do convenient value for the, well, I guess we could do convenient-ish values. We could try to pick some values that don't make zeros, but make things close to zero. You know, so you could do any number of things. There's several ways to go. This one seems simple enough to multiply out and just go with the regular system approach. So let's do that. Let's just multiply this out, and then we'll equate the corresponding coefficients. So we'll FOIL this out. And we have that. On the left-hand side, I'm going to write this in descending order just so that we can sort of talk about the coefficients a little bit more systematically. So the first thing we do is look at the coefficients of the square terms. So the coefficient of x squared on the left, -1. So we're going to build a system here, 3 equations. We have 3 unknowns, so we need 3 equations. We have 2 unknowns, 2 equations, 4 unknowns, 4 equations. N unknowns, n equations. So -1 is the coefficient of x squared on the left. Coefficient of x squared on the right, we see ax squared plus bx squared. So you can think about factoring out x squared from these 2 terms, and your coefficients a plus b. So that will be our right-hand side for that equation. Now we're going to look at the linear coefficient. So the linear term, x to the 1, that's our linear term. Look over on the right. We're going to look at all the coefficients in front of x. And on the right, we are going to end up with b plus c. Let me stack the letters. It's easier to solve the system if you stack the letters. And then the constant term. So our last one is the constant term. So on the left, we have a constant term of 0. On the right, let's see, there's a constant and there's a constant. So now we're going to create the equation 0 equals a plus c. We have that. So there is our system. We just need to find a, b, and c by solving that system. So Any questions? How we build the PFD equation, how we build the system? Any piece of that that's not clear yet? At this stage, whenever you have a system, a linear system, you can use two techniques, elimination or substitution. In this case, substitution often is a little bit longer with these bigger systems. Elimination usually is, a little bit quicker. The main idea here is that we want to eliminate a b or solve for b and substitute in whatever your favorite technique is. Doesn't really matter. So what I'm going to choose to do, again, this is your choice. It's your choice. I see that the top two equations, I could eliminate b. So I'm going to eliminate b by subtracting. Or you could multiply by -1 and add. You can multiply any equation by a constant if you want, a non-zero constant. Your approach could also be, hey, look at these c's. We could eliminate the c. Regardless, we're going to end up with two equations that have two unknowns. That's kind of our goal. Right now we have three equations with three unknowns. If we can reduce that to two equations with two unknowns, then we can use substitution or elimination again. So I am going to take, let's see, I'm going to do equation 2 minus equation 1. That's going to be my choice. You have lots of choices. Does not matter. So 1 minus -1 is 2. All right. 0a minus 1a is minus a. B minus b is 0. C minus 0 is c. So we have that equation. And then we're going to keep the bottom equation so that we now have two equations with two unknowns. So we eliminated b from the top pair. Now if we add those equations together, we will eliminate a. So this, if we add the equations together, 2 plus 0, -a plus a, c plus c. Now we have that c is 1. And once we get c, back substitute into either of these equations. This equation's simpler. Plug in 1 there, subtract it, we see that a is -1. Now, come back over here, we need to solve for b. Doesn't matter which equation we go with. If we use the top equation, we'll plug in the a right here of -1, which will make b equal to 0, because -1 and -1, so -1 is equal to -1 plus 0. Or you could take the c equals 1 and plug it in right here. Let's see what into this equation. If you plug in c equals 1 right there, subtract the 1s, you get b is equal to 0. Doesn't matter. Whatever your favorite equation to plug back into is, we get our 3 constants now. So make sure you can solve your systems, relatively quickly. Practice your elimination or your substitution, whatever makes the most sense. There's no best way. The best way is the way that you understand the easiest without any brain fog. All right, so now this integral can be rewritten as the integral from 0 to 1. And we have a over x plus 1, so -1 over x plus 1. And then we have plus, maybe that's going to turn to a minus, we'll find out soon. So we have bx plus c. Let's see, b is 0 and c is 1, so 1 over x squared plus 1. Ah, that actually worked out pretty nicely. And then dx. So that is our new integration. Way easier than this thing. And it's PFD breaks your one sort of really complicated integral usually into nice bite-sized pieces. So the first one is in log form. So that's minus natural log absolute x plus 1. And the second one is in arctan form. And that's our basic arctan. So plus the arctangent of x, and this is going between 0 and 1. Notice that this 0 is not going to contribute anything, because if you plug it into the first term here, natural log of 1 is 0. If you plug it into the second term, arctangent of 0 is also 0. You've seen the arctangent function quite a bit this semester. The arctangent function goes right through the origin. And so the arctangent of 0 is 0. All right, that's great. So we really are focused on that upper limit of integration. That upper limit of integration is going to give us minus the natural log of 2 plus the inverse tangent of 1. And what is inverse tangent of 1? 5/4. Inverse tangent of 1 is the angle on the right side of the unit circle. Angle on the right with a tangent value of 1. The angle on the right with a tangent value of 1 is at 45 degrees. We use radians in calculus, so that's pi divided by 4. If you wanted to get rid of this negative coefficient, you could. You do not have to. But if you wanted to showcase your log properties, what would that turn into? Log, natural log of what? Natural log of 1/2. Okay. So if you wanted to get rid of that negative inside just because that was what you wanted to do, you could do that. Coefficients can fly up into exponent position. One of our basic log properties. Don't have to do that though. But sometimes when you look at the answer key, they'll do log properties and you're like, wait, how did they get there? Usually it's a log property if it's not obvious. All right, any step there that you want to talk about? So these evaluations of arctan, practice those, make sure you have your unit circle down, make sure that you're sort of, anytime you see an inverse trig function, the first word that should come into your mind other than eq is angle. Anytime you see an inverse trig function, you should be saying to yourself angle. Inverse tangent is on the right, inverse sine is on the right, inverse cosine is on the top. So inverse cosine is between negative pi and is between 0 and pi. So when you're seeing these inverse functions, this is what should be in your mind. You have all three of them here. Hopefully this is clear by now, but inverse cosine, inverse sine, and inverse tangent. That's what you should be seeing when you come across these. This should be the first thing that comes to mind, is that you are dealing with an angle that's restricted to 0 to pi, minus pi over 2 to pi over 2, minus pi over 2 to pi over 2. The one difference here is that these points are excluded, whereas these points are included over here. So that's what you should be thinking when you see an inverse trig function. Restricted angle. All right, the last one for this stuff, and then we'll get to the abstract improper integration. Sometimes doing improper things is fun, even when it's involving integration. So we're going to find the volume of this solid. We're rotating or revolving this region around the x-axis. We could certainly use symmetry here. This object is symmetric about the y-axis. Whenever we have symmetry, it's a nice shortcut. Having a limit of integration that's equal to 0 is, never a bad thing. So the volume here, well, let's go with area first. Remember that if we rotate around an axis and we are touching the axis of rotation, what is our cross section going to be? Disk. If the region touches the axis, if we go perpendicular here, our cross sections will be disks. If there's a gap between the region and the axis you're rotating around, then you're going to have a washer. Exactly. All right, so we're going to draw our vertical integration element, and we're going to draw it. We say that it's at a random x. When that rotates around, it's going to create this disk. And we know that the area of a disk is pi r squared. That's the area of a disk. So our volume, to get volume, we integrate the area function. Now we're going to first put a 2 out in front because we're using some symmetry. So this is by symmetry. So 2 times. And then we're going to integrate from 0 to 1 the area function, which is pi r squared. R in this case is the function. So r is right there. R is the function, which is 1 divided by the square root of 4 minus x squared. And dx. That gives us volume. Integrate area. So when we see this integrand, right there, down in the square root area, we see a difference of squares. Question? Oh, thank you. Thank you. I noticed it just as I was starting to talk. We have to square the r. We have to square the r. And the reason that it struck me that something was off is because what are we doing in this section? We're doing PFD, partial fraction decomposition, which involves factored denominators. And I was looking at that square root, and then all of a sudden it occurred to me that, wait, we're supposed to do PFD. There's a square root. We can't do PFD with the square root. So something was missing. So yeah, we have the r squared. The r squared. Good catch. So 1 over. When we square this, we get just 4 minus x squared. And that's factorable. Now, we have a choice here. We've been doing our PFDs almost always with descending order of our factors, like x squared plus a constant or whatever. We could factor out a -1 so that when we factor this, we actually have x minus 2 and x plus 2 instead of 2 minus x and 2 plus x. It's not going to matter. A linear factor is a linear factor. But you could factor out the -1 if you want. It does not matter. So let's come off to the side. We have the quantity on the inside. Let me use a different color than green since I use green for something else. So let's take the fraction on the inside, 1 over 4 minus x squared. We're going to factor that. We have that. Both of those are linear. So this is a quadratic factor here, but it's not irreducible because you can, in fact, factor it. So it's not an irreducible. We don't do a linear in the numerator. We break this apart into 2 of these. 2 of these partial fractions. Linear denominators, constant in the numerator. And that's going to lead us to our PFD equation. If we focus right here, we're going to multiply both sides by the denominator on the left, creating a 1 on the left when you multiply by that denominator. And then when we multiply the other side by that denominator, we've got this double factor. Multiplies here, the 2 minus x's will cancel, and we're going to be left with this, a times 2 plus x. And then that double factor gets multiplied by this second term, and the 2 plus x's cancel, so we'll be left with b times 2 minus x. So that's our PFD equation. Both those factors are linear, so what's the best technique here in terms of solving for those constants? Yeah, we're going convenient value method since both are linear. Convenient value method, when you have all linear factors, makes the most sense. So our convenient values are the zeros of the denominator. The zeros of the denominator are 2 and negative 2. So we'll choose those. This equation, there's no division here. This equation is defined for every x value. There's no division by 0. So we can plug in whatever we want. We're going to choose 2. And then we're going to choose negative 2 because that will cause zeros. So the equation, if we plug in positive 2, this term goes to 0. This term goes to 4a. That allows us to solve for a. A will be 1/4. Now we're going to plug in negative 2 for all the x's that we see in that equation. When we plug in x equals negative 2 here, we get 2 minus 2, which is 0. That term goes away. There we get negative 4. The left side, there's no x, so it just stays at positive 1. Negative 2 in here, 2 minus minus 2 gives us 4. B. So B is a 4th also. So this allows us to rewrite our integral. We're going to have 2 pi on the outside. Integral is still 0 to 1. This is our new integrand. Both of those are 1/4, so we could, well, let's write it in there first, and then we can factor it out in a second. So we're going to have 1/4 over 2 minus x plus 1/4 over 2 plus x dx. All right. What form are those two fractions in? They're in what kind of form? Log form. Will we need RCR? Yes or no? Will we need RCR? The only time, they're both linear. The only time we need no RCR is if the derivative is 1. If the derivative is any number other than 1 for that linear expression, we have to divide by that derivative. So is there one of them that we do need RCR for?
2 minus x.
The derivative of this one is negative 1, so we're going to need an RCR for that one. Now if we had factored out the minus in the beginning and had our denominator as x minus 2 and x plus 2, then no RCR because both derivatives would be plus 1. Here we are going to need an RCR. So we have 2 pi. Let's put some big brackets here. Oh, let's factor out that 1/4 first, actually. So 2 pi divided by 4. 2 pi divided by 4, factoring out that 1/4, and then our bracket. All right, so the first one is going to be natural log of the absolute value of the denominator. And then RCR says divide by the derivative of that linear factor. Plus natural log absolute value 2 plus x. Don't need an RCR there because the derivative is positive 1, so we don't need to deal with it. And then our limits of integration are 0 to 1. Let's Let's simplify out front. We have pi divided by 2. And then inside, we're going to first plug in 1. So plugging in 1 right here. 2 minus 1 is 1. Natural log of 1 is 0. So this term is gone when we plug in the 1. This term is natural log of 3. We don't need absolute value bars. 3 is positive. So there's the upper limit of integration minus the antiderivative at the lower limit of integration. So minus, maybe I'll use a bracket still because we're going to have to subtract off all this. Might be easier not to distribute the minus until after we write down. So it's upper limit minus this whole thing evaluated at 0. Plug in 0 here, we get ln 2 divided by negative 1. So minus ln 2 plus, plug in the 0 there, we get ln of 2. So those two subtract each other away to nothingness. And we're going to be left with a final answer of pi ln of 3 divided by 2. That'll be the volume of our solid. Yeah.
Where did you get the negative one?
This negative 1, so that is the RCR, that is the derivative of this. So whenever we're integrating and we have, so let's suppose we have e to the negative x plus 1 dx. This integral is e to the negative x plus 1. Integral of an exponential is itself, but then if the linear expression that you're using has a derivative that's not just 1, then you have to divide by that derivative. So if this was 2 minus 3x, we would divide by negative 3. So we're dividing by the derivative of the linear expression. So we only use RCR if we have a linear expression. Otherwise, we'd have to go to regular substitution or some other technique. But if we use RCR, it's because we have a linear expression in the exponent, in the angle, in the log, in the square root, and then we divide by that derivative. Other questions on it? So that is RCR. Reverse chain rule. Reverse chain rule, we're dividing instead of multiplying. And we have a reverse chain rule. The reverse chain rule is for integration. All right, what do we think? Any other questions on that? The setup, disk method, pi r squared. All right, you ready for some abstract math?
No.
No! Let me ask you a simple question that involves arithmetic. Let's just suppose you like adding numbers, because that's your jam. You like adding numbers. If your bag of numbers that you're going to add together is infinite, so you have an infinite collection of positive numbers just hanging out in your bag, can you add your infinite collection of positive numbers and get something that's finite?
Mm-hmm.
Whoa!
Hermione's books.
Why? How can you do that? Give me an example.
Do you remember the first part of Deathly Hallows? They're
The
out
first
on
part of
literal
Deathly
streets.
Hallows.
And,
Yes.
And then she goes,
Yes.
that'll be the books.
Yep, okay. So if you know it from Harry Potter, that's great. We can also think of some other things that you have seen over the years. Like, for example, if you add 0.3, that's a positive number, and if you add 0.03 to that, that's a positive number. So most people's instinct when we say add a collection of positive numbers together is that, oh, well, the sum's got to be infinite, right? Because you imagine blowing up a balloon, and if you did that an infinite number of times, eventually the balloon's going to pop, right? Most of us think, oh, adding an infinite collection of positive numbers is going to be something infinite. You're not going to be able to get something finite. But this example should make it crystal clear that, oh, every one of these terms is in fact positive, correct? They're all positive. There's an infinite number of them. And we all know that when we add those together, we get what finite number? What was that?
10 over 3.
Not 10 over 3.
1/3.
1/3. We get 1 over 3. 1 over 3. So we get 1/3. So this is equal to 1/3. All right, and there's a bazillion examples like this that we could come up with, 0.9 plus 0.09 plus 0.009. Well, let me ask you that one actually, because this one's got a slight twist to it. So if you were to add these numbers up, what do you get?
0.999.
What about as a, is that a rational number, 0.9 repeating?
Just 1.
You should go like this. Yes, it's a rational number, right? A rational number, if you look at it in decimal form, it's repeating or terminating. So 0.9 repeating is a rational number. Anything that's a rational number can be written as a ratio of integers. 0.9 repeating is not a ratio of integers. So if we write it as a ratio of integers, it becomes what you just said, it becomes 1. So this is 0.9 repeating, which is the same thing as 1, which you could think of as 1.0 or just 1 divided by 1 or whatever. You can think of it as a fraction or as a decimal. So one thing that you can talk about is that the decimal expansion of numbers is not unique, because 0.9 repeating is the exact same number as 1.0. If two numbers aren't the same, it means there's a measurable distance between the two, and there is no measurable distance between 0.9 repeating and 1. If you say, oh, the difference between the two is a decimal point with 50 zeros and then a 1, I'll say, no, it isn't. I can show you that it's not. So there is no discernible distance between 0.9 repeating and 1, which means they're the same number. It's just two different names, name and nickname or something. So the moral of the story here is that you can, in fact, add an infinite number of positive terms together and get a finite result. Obviously, that's not always the case. Like if you add these together, this clearly goes to infinity. If you add 1 to itself repeatedly. What about if you add, say, 0.1 to itself repeatedly? What's that going to be? That's also going to be infinity. If you take any positive number and add it to itself an infinite number of times, you will get infinity. Right? That cannot be finite. If you add the same exact quantity to itself forever, it's going to blow up. It's going to go to infinity. All right? And then here is the super classic that we will talk a lot about between now and the end of the semester. How about that? One thing that should be obvious from up here is that the only way we can end up with a finite result if we're adding an infinite collection of positive numbers together is if we're adding less and less and less and less, so that when we're out in the tail of the summation, we're essentially adding 0. We're adding something that's so close to 0, it doesn't create a number that's going to infinity, a sum that's going to infinity. So what must be the case if we're going to have this infinite sum, aka infinite series, what must be the case is that these numbers have to be going to 0. The terms out in the tail must be getting closer and closer to 0. It's the only way, otherwise we'd have the balloon exploding situation. So when you look at this, we say, oh, the terms are going to 0. Therefore, it might be finite. We'll use a word called converge. It might converge, but it doesn't necessarily have to. These terms, not only do they have to be going to 0, they have to be going to 0 fast. And if they're not going to 0 fast, which we'll talk about what that means, that's what this chapter is all about, this section. If they're not going to 0 fast, then it will still diverge. This one we will show diverges. In other words, the sum is not finite, the sum doesn't converge, the sum is infinite. There's a million ways to say it. But if we jack this up and we say, hey, let's take the squares like that, now these fractions are going to 0 faster. These numbers are getting smaller faster. This one will, in fact, be finite. So that's what this section's all about, figuring out that threshold. When are we going to have what we're going to call convergence, and when are we going to have divergence? So that's what we're dealing with. Now, this is a discrete description that I've just talked about. All right? And we're going to get to that specific discrete idea in the next unit. Here, we're going to be talking about areas. But whenever we're talking about areas, we think in our mind of subdividing into rectangles, which puts us into that situation. Right? When we're trying to find the area under a curve, you should be envisioning, all these rectangles, and as the number of rectangles increases, our Riemann sum becomes an integral, blah, blah, blah. So you can always think of the area beneath a curve really as an infinite sum. You can think of it that way. You have an infinite number of rectangles, they each have an area, the area is a number, you can add them all together and see if it's finite. So here is where we are then. We've built some intuition. You can add an infinite collection of positive numbers together and get something finite. So now that you at least believe that, now the extension of that is this. What about if we have an unbounded area? So area being unbounded means what is the area of this entire tail that never ends? It's unbounded. A region in the xy plane is bounded if you can draw a circle around it. But this region is going to go on forever and ever and ever and ever. So that region is called unbounded. We don't say that the region is infinite. We say the region is unbounded. And that unbounded region may have finite area or it may have infinite area. Right? Just because the region goes on forever doesn't mean that the area is infinite. So we want to use the word unbounded when we've got this region that goes on forever. Unbounded. You can't put a circle around it. So it's unbounded. And it depends. What we need to figure out is the same thing that we just built some intuition with. This tail, that curve, needs to go to the x-axis fast enough. And that's what we're going to figure out. How fast means fast. How fast does it need to go in order to get convergence? So we have to figure out that threshold. Is it not going fast enough? Then we have divergence, and the area is in fact infinite. If it goes to the x-axis fast enough, then the area is finite, even though it's an unbounded region. Okay, so here's what we do. We all know about definite integrals, And so what we're going to do is create a definite integral that's going to find the area between A and B. So that's what this is right here. This is a definite integral. That integral is definite. You know how to do it. You integrate f, you plug in the b, you plug in the a, you take the difference, fundamental theorem of calculus. But if this is a variable out here in your upper limit of integration, you end up with a function with a b in it. And then you take the limit as b goes to infinity. So to find this unbounded area, we take a chunk in the front. That's a definite integral. It's going to create a function that builds the area out to whatever b is. And then we take the limit as b goes to infinity, and that will be our strategy. Similarly, if our horizontal tail is to the left, we're going to create a definite integral. All right, this is a definite integral, finding the area between a and b right there. We can do that. But we're going to end up with a function of a. And then we will let a travel to negative infinity. We're going to take the limit of a definite integral. So that definite integral is hopefully going to give us a polynomial or some function we can take the limit of easily. And then we'll let a go to negative infinity. Third possible case for this horizontally unbounded, the worst case is if both tails are unbounded. Unbounded, can't put a circle around it, goes on forever in two directions. What we have to do is pick some midpoint. Does not have to be 0, it can be any number you want. And what we do is treat it separately. So we're going to have one integral that's an improper integral for this side, and then another improper integral for that side. And in order for this unbounded bell curve to have finite area, both of those tails have to be finite. If one of the tails is infinite, the total sum is infinite. If you have an infinite tail on the right and a finite tail on the left, finite plus infinite is infinite. The only way you can get finite is if it's finite plus finite. And it doesn't matter where you split it. And you have to split it into two integrals. You can't use some weird symmetry and, like go from 0 to a and then double it. You can't do something. You have to break it into two separate integrals. All right. So that's the overview. So let's get a little more specific. Let's take a look at this example here. So determine if the unbounded area between the x-axis and the curve is finite or infinite. So the light gray is representing that unbounded area that goes on forever. The dark gray is representing the finite area that we can find as a function of b. So let me show you how that looks. So let's suppose the curve is 1 over x squared. So all of these curves that are 1 over x squared, 1 over x cubed, 1 over x to the fourth, 1 over x, right, they all look the same. They're all zipping down to the x-axis with slightly different steepnesses. But they all have that general shape of a slide down to the x-axis. So if we want to integrate 1 over x squared from 1 to b, let's just imagine b is some number bigger than 1, and so it's just to the right of 1. This is what we would do. If we're going to integrate from 1 to b, okay, x to the negative 2, we add 1 to the exponent, we divide by the new exponent, we do our regular power rule. We get negative 1 over x from 1 to b. This is the function of b that tells us what that area is. If you plugged in b equals 1, you get 0. The integral from 1 to 1 is 0. If you plug in b equals 2, so if we were out here between 1 and 2, what do we get for our area? So if we were going to integrate from 1 to 2, what's the area? So if b is 2, the area will be 1/2. If you plug in b equals 2, you get negative 1/2 plus 1, which is 1/2. So if b was 2, the area would be 1/2. If b was 3, so if we were going to integrate from 1 to 3 under this curve, we would get 2/3. we get 1 minus 1/3. If we were going to integrate from 1 to 4, we would get 3/4, right? 3/4. Everyone following? And so this is a function of b that represents the area between 1 and b. That's a function. We know how to take the limit of a function. So we're going to take that function that represents the area, definite integral, take the limit as b goes to infinity, and we get 1. That's a finite number. That tells us that that unbounded area actually is finite. That unbounded area is 1. The area of the entire tail is 1 square unit, whatever your units happen to be. Okay? So that's the strategy. Form a definite integral as a function, take the limit of that function. Boom. That's it. But it's a big deal. We're finding the area of an unbounded region, which is not trivial. All right, here is an example with an exponential function. That's an exponential decay function. When we have a horizontally unbounded tail, so we call these improper integrals. Right, we've already had all these other integrals where you have numerical values or variables in the limits of integration. If you have an infinity in one of the limits of integration, that's improper. Right, that's sort of next level type of integral. And so this integral is representing the area beneath the curve from 1 to infinity. Does it look like that curve approaches the x-axis fast? Yeah. We are only out at 6, and it's already like the curve and the x-axis are indistinguishable. So most likely, that's a finite area, because you can see from the graph that it's approaching it fast. That's just sort of our intuition. We also know from algebra that exponential functions either grow fast or decay fast, much faster than polynomial types of functions. So our instinct should be that, yeah, it's probably finite. I mean, look at that little tiny area. So, improper integral, the very first word that you write down with an improper integral is limit, as depends on the letter. Usually for an upper limit of integration, we use a b. So we're going to create this definite integral from 1 to b. So that's a definite integral. It's going to be a function of b, and then we just take the limit of b, limit as b goes to infinity. All right, so first we have to integrate that exponential function. That exponential function has one little twist. It's not e to the negative x. It's an exponential function with base 2. So we have to remember the little tweak, which you should have learned in Calc 1, when your base is not e. So the integral of an exponential, the first thing we do is itself. For any exponential, integral or derivative, first step, itself. We see a reverse chain rule in there because the exponent is linear, but the derivative is not 1, so we have to divide by the derivative of that linear exponent. So we do that. And then we know that we have to do something with the 2 because it's not an e. Anyone remember what to do? If your base is not natural, how do we adjust? Any ideas?
Is it just natural log of 2 or no?
So there is a natural log of 2, and the question, similar to the reverse chain rule, is do we multiply by it or do we divide by it when we're integrating? What do you think if we're integrating? Divide. So we're going to adjust this with a natural log of 2 right there. So that is our antiderivative. We are going from 1 to b. So our next step is pretty straightforward. We're just going to plug in. And if we wanted to, we could factor out this constant right here. It does not matter. I usually do factor it out. I just didn't in this case. It does not matter. All right, so there's the upper limit of integration substituted into our antiderivative. And then we're subtracting off the antiderivative evaluated at the lower limit, so it's going to become a plus instead of a minus. We're plugging in a 1. So we get that. And we're taking the limit of all that as b goes to infinity. Most of us, when we see negative exponents and we're trying to take limits, most of the time, most people find it way easier to modify that and put that quantity in the denominator and have a positive exponent. Usually, it's easier to evaluate limits that way. And then this is going to be 2 over natural log of 2. So, the limit as b goes to infinity, what's going to happen to this term here? What is happening to this term as b goes to infinity? That's going to
That.
go to what? Go to what?
It's gonna go to that.
Use words. Go to what? Go to, that term's going to go to? What is the blue going to go to? Right, the denominator is going to infinity, so the fraction is going to 0. Yes, going to 0. And so then our overall limit is this, and that tells us that the area is in fact finite, and that is the area of that tail. That is the area of that tail. All right, take a break. Let's take 10. I can't take any more of this. I need a break. Take 10, take 10. Think about unbounded regions that have finite area. Welcome back. No,
Today we
I'm just confused.
Oh my god, what the fuck am I
X squared plus 100. That way I know what it's gonna be, because this one, that would just be 10. But in this case, now this one is just 100 X squared plus 100.
All right, so here's another example of a horizontal one. I want you all to try to set this one up. The one difference is that we're going to the left instead of the right. It's still a horizontal tail. We're still trying to find out whether this region here is that unbounded region, whether it's finite or infinite in area. So see if you can set up and integrate this. And then if you forgot about the non-natural base for an exponential over here, I remind you how to find the derivative of a non-natural exponential. And for a non-natural exponential's derivative, you multiply by the natural log of the base. When you integrate, you divide by the natural log of the base. So see if you can find the area of that yellow region. This book will always use an A if the lower limit is the infinite limit, and a B if it's for the upper limit. So A to the left, B to the right, but it doesn't matter. You can choose your favorite letter.
I'll do it.
So that is our case right there. That is us. Questions? Oh. I know the pain. So the integral of an exponential is itself. And we divide by the negative exponent. And then if the base is not e, if you were to take a derivative of an exponential where the base is not e, the derivative will end up being itself times natural log of 2. But if you're integrating an exponential where the base is not e, you'll divide by natural log of 2. So that anytime the base is not in e, then you have this extra division by natural log of whatever the base is. And that's, you prove it through this implicit differentiation.
No sé qué está diciendo. Dile al profe que te diga cómo se saca el de no sé cómo se mira, no sé. Ah, sí, sí, sí.
So that's the first step that we want to recognize. We have the A, we're thinking in our mind that the A is somewhere out here. And so we're going to find this area from A, that's an A, from A over to 0 is a definite integral. So from A to 0, that's what this is finding. And in order to integrate this quantity that's in the denominator, we pop it up to the numerator and change the sign on the exponent. So that is our definite integral. This in here is going to be a function of A. And then we just take the limit of A as A goes to infinity. So this should be this is our setup stage. Anytime we have an improper integral, the first word is limit. We always have to write limit first. And then we'll do the definite integral part. So this we will have to use reverse chain rule. That 2 minus x has a derivative of -1. So we have to use reverse chain rule. So it's going to be 2 minus x to the 2/3 when we add the 1. And then we divide by 2/3, which means multiply by 3/2. And then the reverse chain rule says divide by the derivative of the inside, so we want to put a minus sign out in front. So that part's the reverse chain rule. Add 1 to the exponent, divide by the new exponent, divide by the derivative of the inside. And this is going to go from A to 0. And then let's factor out the 3/2 this time, that -3/2. And we have already established that the limit is as A goes to -infinity. I'm totally fine if you don't write that on every step. We'll rewrite it again at the end when we're about to take the limit, but you don't need to write it on every single step if you don't want to. So then here, we're plugging in 0. So we're going to have 2 to the 2/3 power. Plugging in 0. And then we subtract off, maybe I'll make this a bracket since we're going to have parentheses on the inside. So 2 to the 2/3, plugging in 0, minus the quantity 2 minus A to the 2/3 power. And that limit is as A goes to -infinity. Maybe I'll put that in now because we're going to start thinking about that. All right, so everybody okay with that setup there? So, when we think about evaluating at -infinity, this 2 to the 2/3 is just a constant. It's an irrational number. Who knows what it is? You know, 3rd root of 2 squared, or you could make it the 3rd root of 4, whatever. It's just a positive number. And then we subtract off. And we have to think to ourselves, what's happening in here first? So as a is going to negative infinity, I find it helpful to put little brackets and kind of do this like an onion. Start on the inside and move out. Isn't this part inside here going to positive infinity? All right, so 2 minus infinity. So just that part's going to positive infinity. So now we're asking ourselves, what happens to this part? So if I'm ignoring the minus sign, I just want to sort of get the next step out is this exponent. So now we're thinking about a number that's going towards positive infinity, and we're raising it to the 2/3 power. That's a fractional exponent. And in your mind, when you have these fractional exponents, you should be thinking of some sort of bird wing thing, right? The square root of x, the third root of x, anytime the rational exponent is less than 1, you're thinking bird wing. It's always going, you can reduce it down to the simplest bird wing, a square root of x. It's always going to look like that. And the key is that that's going to infinity, right? It's going to infinity. There's not a horizontal asymptote. So if we take a number that's going to infinity and then we raise it to the 2/3 power, the further out we go, that 2/3 power is still dragging that number towards infinity. So this is also going to infinity. And if you want to put a little arrow, you can, but it gets a little messy, so I just sort of try to simplify it as much as possible. Now we can do the subtraction, and this, if we do the subtraction piece, we are dealing with, oh, let me say one more thing before we deal with that. So, oh no, because that's positive infinity. Why we're, oh, there's the negative. I'm stressing out because it was going to be negative infinity, and it can't be negative, it's area. But I forgot we pulled out a minus. So we'll offset it and make it positive. Okay, so let's do that, do what I had suggested originally. So now we include the minus sign, and now that's negative infinity. 2 minus infinity is negative infinity. So if we just keep going out one stage at a time, it's still negative infinity. And now we have a negative constant times negative infinity, which will give us positive infinity. Remove that graph, we don't need that. So this will be positive infinity. That area is infinite. So that area, which is unbounded, can't put a circle around it, that area is infinite. And when we look at the graph, we can kind of see the difference. The curves that have finite tails, I shouldn't say they're obvious, but you can tell that there's a more likely chance that that's finite because it goes to the x-axis faster than this is going. So you can kind of tell. So we get positive infinity for that. So that area is infinite. Any questions on any of those steps? All right, let's take a look at more. So if we have, we're going to do one example of the double tail. They are a pain because you are basically doing 2 problems in one. You have to separate it into 2 integrals. And you can't like do some symmetry thing and say, oh, I'm going to take the limit as a goes to infinity and make this negative a and positive a. You can't do that. It's got to be separated into 2 separate integrals. The most natural place to separate, of course, is at 0, because then we know that if you have 0 as a limit of integration, it's usually better. So if you can, so we're going to separate it right there. Does not matter what constant you separate it at. It's just that 0 is easier in the manipulation of an integral. So we have to bust this into 2 integrals. So 1 improper integral becomes 2 improper integrals, and then we become 2 limits. So we're going to make this negative infinity to 0 of this. Is that quantity factorable? And then 0 to infinity. Is that denominator factorable? No?
I don't know, we have to complete the square.
Yeah, completing the square. Is that what you said?
Yeah,
Yeah, completing the square. So this is not factorable, right? If we, that constant, if we want to get a 2 in the middle, everything's positive, it'd have to be x plus something and x plus something. There's no two positive numbers that multiply to 5 and add to 2. So not going to be factorable. So we will complete the square. Now let's go down here. So now we have to create a limit for each of these. So we're going to need a limit as a goes to negative infinity. So they always will do a to the left. So a going to negative infinity. And this will be the integral from a to 0. And let's go ahead and write this as a perfect square trinomial. What's the constant have to be for this to be factorable as a perfect square trinomial? Divide by 2 and square, so it's got to be 1. And so we'll pull 1 off from that 5. And then this will be the limit as b goes to infinity. Same exact integrand, x squared plus 2x plus 1 plus 4. And then let's go ahead and factor. So we're going to have this set up. X plus 1 squared plus 4 plus limit. I forgot my integral symbol here. And I forgot it again here. I'm not forgetting it there. Okay, I think we have it all in here. So this one is as a go. This one is a to 0. This one is going to be 0 to b. Let's get all the pieces in there. This one is as b goes to infinity. This one is as a goes to negative infinity. So that is our breakdown into 2 separate improper integrals. One for the left, one for the right. I really want to factor out that 4 right there so that it's a 1 and we can turn it into a basic inverse tangent integral. So we will factor out that 4 in the denominator. So it's going to come out. There's no square root. There's no power on that 4. So it's going to come out as a 4. So we're going to have 1/4 limit. So we're on this one right there. So that says a goes to negative infinity, which again, you don't have to write it on every single step, but a to 0 dx. This is going to be x plus 1 divided by 2, quantity squared plus 1. And then this will be a 1/4 limit as b goes to infinity. 0 to b, same exact integrand. So x plus 1 divided by 2, quantity squared plus 1. So now we have 2 arctans, 2 basic arctans. The substitution piece here, the RCR piece here, we look in here, that's linear. And what is the derivative of yellow? What is the derivative of x plus 1 divided by 2? 1/2? So x plus 1 over 2, you're thinking of that as 1/2 x plus 1/2. Derivative is a half. So we'll have to multiply by 2 when all is said and done. So this will be the inverse 1/4 limit as a goes to negative infinity inverse tangent of x plus 1 over 2, basic inverse tan, so inverse tan of whatever's in here, but then the reverse chain rule piece kicks in, so we have arctan of that quantity, and what's gonna go in front is our coefficient. 2, divide by 1/2, so multiply by 2, is that what I heard? There's some rumbling in the hallway. And then over here, same thing, 1/4 limit as b goes to infinity. We have the exact same, I should put the a to 0 evaluation bar there. So we're going to have the same exact thing here. Arctan of x plus 1 over 2 divided by 1/2 means multiplied by 2. And this is going to go 0 to b. Question?
Is the reason why it is the inverse of tangent because on the limit of the integration, that is in tangent form, or?
So we haven't done anything with the limit yet. We're just looking at this. So the integral of 1 over x squared plus 1 is arctan.
Yeah.
Yeah, inverse tan. So we haven't done any limit yet, though. Now we have to deal with all the substitutions. Substitute upper limit, lower limit in both of them. This 2 can factor out to the front in each, right? Constants can come through, limits, derivatives, and integrals. So this is going to be 1/2 limit. This is going to be as a goes to negative infinity. All right, let's plug in the upper limit. So we get arctan of 1/2. Plugging in 0. Minus arctan of a plus 1 divided by 2. So there's the first one. Over here we get 1/2 limit as b goes to positive infinity of arctan of b plus 1 over 2 minus arctan of 1/2. Remind you again, the graph of arctangent. Looks like that. So, limit of a constant, arctan of 1/2 is a constant. The limit of a constant is itself. Right? There's no variable. Let's look at this one. A is going to negative infinity. If you add 1 to that, the numerator is still going to negative infinity. If you divide a quantity that's going to negative infinity by a constant, it's still going to negative infinity. So the inside here is going to negative infinity. When we look at the arctangent function, if we start moving in the negative infinity direction, where does the arctangent function go to? What number does it go to? Negative, not quite negative 1. What are these asymptotes at for arctan? Negative pi over 2 and positive pi over 2. Those are the horizontal asymptotes for arctan. So if this is going to negative infinity, this quantity here is going to negative pi over 2. Right? Arctan of a very negative number is getting closer and closer to negative pi over 2. When we come over here, b plus 1 over 2. If b is going to infinity, numerator is still going to infinity. If you divide by 2, that whole quantity is still going to infinity. And if we look at our arctan function, if the inside of the arctan is going towards positive infinity, the y values are going towards pi over 2. So this whole thing is going to pi over 2. So our answer then, we get 1/2, and then, well, we can distribute this 1/2. So 1/2 arctangent of 1/2 minus, okay, this is going to negative pi over 2, so it's minus a minus, so that's plus pi over 2. So that's going to be plus pi divided by 4. 1/2 times that. And then we come in here, this is pi over 2 times 1/2, so that's plus pi over 4 again. And then we have 1/2 times this quantity, but there's a negative, so negative 1/2 arctangent of 1/2. So So our final answer, pi divided by 2. Because those two cancel out. So that is our cumulative area between underneath that bell curve. If you've had statistics, that should look really familiar. In stats, everything is based on the area beneath the bell curve. But does anybody know what we force the area to be under that bell curve in stats? Force it to be 1. So you create a function that's got 2 tails that creates an area of 1. And then you can do all that standard deviation and variance stuff.
Since in this case, both of the, I guess the intervals are identical right until you hit the limit, could you potentially omit the other one and then only at the end spread it out?
So say that once again. So these integral, so you're saying that both of the antiderivatives look the same. And so could you do what exactly?
Basically, right at the end, set up the full one, I guess, like when you go to actually integrate.
It is, yeah, it's possible to do something like that. You just don't want, you can't factor anything out though, because this goes from A to 0 and this goes from 0 to B. So there's no concise way to sort of combine them into one because the limits are different. You know what I mean? Let me ask you this question. Do you think the pink area and the yellow area are the same? Is the pink area and the yellow area the same? Let's take a look. So let's focus just on the pink for a second. So the pink is this whole one right here. That's the pink one. The yellow one is this one. So when we come down, this is the pink one right here. That one is the yellow one. So this, do you agree that this is the pink area right there? Oh, and I wrote it in yellow though. Do you agree that that's the pink one? Right, that's the pink one. And you agree that this is the yellow one over here. So this is the yellow one. That's the pink one. So you can see that they're different areas, right? This one is pi over 4 plus that inverse tangent constant. This is pi over 4 minus it. So you can see that they do in fact have different areas. What do you think if we split this at -1? Do you think the areas would be the same? Yeah, if you split that at -1, it certainly feels like they might be the same. Feels like they might not have this extra constant there. That would be an interesting exercise. Doesn't look like those tails are approaching the x-axis at the same rate though, does it? Maybe it does. It's kind of hard to see. If you're here, if you pick the center to be right there, and you look over 3 units this way, and you look over 1, 2, 3 units that way, yeah, it looks like those are actually kind of approaching the x-axis at the same pace. So most likely if we split it at -1, we'd see that the areas were the same. But, yeah, so it'd be hard though to combine just because you have different limits. But yeah, I know what you're talking about though, because it feels like we should be able to shortcut that antiderivative step. So you could sort of think about an indefinite integral and then put the limits in later. Yeah, to do that. That could shortcut it a little bit. All right, let's go to a couple of just direct ones. One tail, dealing with 2 tails is a real pain. I wouldn't put a 2-tail one on the test because it's really 2 problems in one, which just seems like too much. When we look at this, one thing we want to do is to try to develop some intuition for whether we should be getting a finite or an infinite area. And so one thing that I want you to notice is that if we go back up here to this first example I did, if you look at the denominator, the power on x here was 2, and we ended up with a finite answer. So the power on x was a 2, we ended up with a finite answer. This one that we're looking at right now, what's the power on x in the denominator? 2. The numerator is a function, but it's a bounded function. When you go out towards infinity, what is that arctan of x approximately equal to? When you go out to infinity on arctangent, it's about equal to pi over 2. So the numerator is a function, but it's a bounded function. And if you go way out to the tail, it's about pi over 2, so it's just a constant. So what should our intuition tell us about this area? Should it be finite or infinite?
Finite.
Finite, because the denominator is power of 2. Numerator is just a constant, so those fractions are going to go to 0 pretty darn fast, because that denominator is going to be increasing at the same rate as the other one that we did that showed finite area. And when we look at the graph, you can kind of tell, oh yeah, that's going to 0 pretty fast. All right, so this is an improper integral, so the first word that we write down is limit, and it's in the upper position, so we're going to say b. So now we have a definite integral that is representing the area from 1 to b. So let's see, 1 is right here. So we're finding this area right there. We'll call, so we have this area right here. We'll call that b, and there's 1. So we're finding that area. That area is going to be a function of b. So function of b. And then we take the limit as b goes to infinity. And that's going to tell us what our final area is. Okay, what technique of integration are we going to use here? Substitution. So the first thing we say to ourselves is, let's go to substitution first. If it doesn't have an immediate antiderivative, that's the first thing. Is it done? Can we do it with u sub? Well, we decide whether we can do it with u sub or not if there is a function whose derivative is also present. And the derivative of arctan is 1 over 1 plus x squared, so O, or 1 over x squared plus 1, doesn't matter how you write the denominator. Right? So we see the derivative of arctangent is there. So u substitution is going to work really nicely here. If we let u be arctan of x, then du is 1 over 1 plus x squared dx. So this is just the u du. U, right? Okay, so we have limit. This becomes u du. The limits of integration, we're going to just hold off. We'll just wait. We'll go back to the original limits. So this limit is as b goes to infinity. Limit. All right, so integral of u squared over 2. U squared over 2 with our placeholder limits. Don't want to deal with this substitution thing. Let's go all the way back. So we're going to have 1/2 limit, and we are back substituting the arctangent in here. So that's going to be arctangent, and I factored out that 2. So this is arctangent of x, quantity squared. Now we're back to the x limits, 1 and b. Plug in the upper limit of integration. B is going to go to infinity, so we're going to have arctangent of b quantity squared minus arctangent of 1 quantity squared. So, take the limit. Arctan of b as b goes to infinity. Arctan approaches pi over 2 again. So this is going to be pi over 2 squared. Pi over 2 squared is pi squared over 4. And we've talked a lot about this one. Arctan of 1, angle on the right, tangent of 1, that's pi over 4, but we squared, so we get pi squared over 16. That will be our answer. Get a common denominator to merge those two terms together. Common denominator of 16, multiply by 4 and 4. So we're going to get 4 pi squared minus 1 pi squared. That's 3 pi squared. Divided by the common denominator of 16, but then we double it to make it 32. And that will be our final answer.
So is the reason why the inverse tangent of b is pi over 2 is because b is going infinitely, but it will never go past pi over 2. So we just say that it's going to be pi over 2.
That's that's what a limit means. So if we have, when we're looking at that graph of arctangent, this horizontal asymptote is pi over 2. And so as we start moving this direction, the value of inverse tangent gets closer and closer and closer to pi over 2, which means the limit is pi over 2. So that's what the limit of a function means. It means what number, if any, is the function getting close to or equal to. So in this case, it's getting closer and closer to pi over 2. So that is the limit of it.
Okay.
The limit of it is pi over 2. Even though its value is never pi over 2. Its value is always a little less than pi over 2, but its limit is pi over 2. All right, so our intuition, denominator's power was a 2. That gave us convergence. Let's look at one where the denominator is 1. See what happens. So we have the limit, again, as b goes to infinity. Limit 1 to b, limit as b goes to infinity, integral 1 to b, and this is dx over x. And what's the integral of 1 over x? ln of x. So we get ln of x from 1 to b. And when you look at the graph of that, it looks like that graph is definitely not approaching the x-axis with a lot of speed. With those other ones, the x-axis and the curve kind of became one, right? They sort of were indistinguishable. So we're kind of suspecting that things will be different here. Natural log of b minus natural log of 1. What's natural log of 1? 0. So we end up with limit of natural log of b as b goes to infinity. And what is the limit of ln b as b goes to infinity? Infinity. Right? If we look at the natural log function, that function kind of looks like a bird wing, but it goes through 1 instead of 0. That's what the natural log function looks like. Limit as x goes to infinity is infinite. So this tells us that we have infinite area down here. So when we find the area here, this area is not finite. When the power in the denominator is only 1, that's not enough. That curve does not hit the x-axis fast enough. You're going to have infinite area.
If b was approaching to negative infinity, would it be 0 then? Or it would be just be negative infinity?
So the natural log function, the domain is 0 to infinity. So we can't let this go to negative infinity for this, because natural log of a negative number is undefined.
Okay.
So if we had a different function we might be able to take the limit as b goes to negative infinity, but not for this antiderivative, because log is only defined for positive numbers.
Okay.
Make sense?
Yeah.
Right, log, you can't take the log of a negative. Log of a negative is undefined, because there's no graph over here. Okay, so let's talk about Gabriel's horn. So this classic Calc 2 topic, Gabriel's horn, is created by taking the function 1 over x that we just dealt with. 1 over x has infinite area beneath it. Gabriel's horn is created by taking 1 over x from 1 to infinity, rotating it about the x-axis, and it creates this horn-looking thing. So it goes forever, though. It's unbounded. So it goes forever this way down. Let's first find the volume of Gabriel's horn. The volume is very easy to find because we can use the disk method. We can imagine an arbitrary x right here. There's the radius. So we have pi r squared. The radius is the function, 1 over x. So we get pi r squared. That's an improper integral because we're going 1 to infinity. So we're going to focus on the integral first. 1 over x squared is the same as x to the negative 2. That's an easy integral. We add 1 to the exponent and get negative 1, divide by the negative 1. So we get this as our antiderivative, negative pi over x. You can factor out the pi if you want. Plug in the b, plug in the 1. Take the limit as b goes to infinity. As b goes to infinity, this fraction goes to 0 because b is in the bottom. When the bottom blows up, the fractions go to 0. So Gabriel's horn has finite volume. Finite volume in Gabriel's horn. So we have this finite volume of pi cubic units. Finite volume. But remember, we just found that the area beneath 1 over x is infinite. Just keep that in mind. We have that infinite area. Now let's show that Gabriel's surface area, Gabriel's horn's surface area, is infinite. So we're starting with this function. We're going to look just at surface area. We know that the surface area formula involves a 2 pi r, and we know that we need the derivative of the function that we're rotating. The derivative of 1 over x is minus 1 over x squared, and if we square that quantity, we get 1 over x to the 4th. So taking our surface area formula, we don't know s limits, we have to convert it over to x's. We get this. 2 pi r is again the function. 2 pi r is the circumference. And then we have to multiply, we have to convert the ds, square root of that. So here is where we're at. So we just plug straight into the surface area formula, and we're given this right there. And now here is the interesting step. We are going to ditch this square root thing. We're just going to take it away. Take it away, and I claim that if we take that away, the resulting integral is going to be smaller. So we still have the 2 pi. We still have the 2 pi. The only thing that's left is the dx over x. We're just taking away this square root part, taking it out. And I claim that this is going to shrink it. Why? So, if you look right here, first of all, do you agree with that? That square root piece for x greater than or equal to 1, isn't that always bigger than 1? You're taking the square root of a number bigger than 1. The square root of a number bigger than 1 is a number bigger than 1. You only get to a number smaller than 1 if you take the square root of a number smaller than 1, the square root of 0.9, 0.8, 0.7, right? If this number on the inside of the square root is always bigger than 1, then the square root of it's always bigger than 1. So if we take away this number that's bigger than 1, we're going to have a smaller value. All right? Think of it this way. If you have a number, say 5, let's write 5 down here. If you were to multiply this number over here by something that's bigger than 1, isn't that true? Right? So if you have 5 and you multiply it by something bigger than 1, this is going to give you a number bigger than 5. So that's what we're doing. We're saying, well, if we take away this number that's bigger than 1, what's resulting is got to be something that's smaller. Okay? All right. So we just calculated that integral. The integral of 1 over x is infinite. We just did that. The integral of 1 over x, get natural log of x, blah, blah, it's infinite. So the surface area is infinite. So when we look at Gabriel's horn, if you look online or you look in, like I actually have a video of this up here in our weekly videos if you're looking at those. So Gabriel's horn has finite volume and infinite surface area. If it has finite volume, you can fill it with paint. Finite volume, you can fill it with paint. But it has infinite surface area. Can you paint an infinite surface? But if the horn is filled with paint, isn't it painted? So think about this before Thursday. How do they call this Gabriel's paradox? If it's got finite volume, you can fill it with paint. If it's got infinite surface area, you can't paint it. But if it's filled with paint, it's painted. With leftover paint. Because the whole thing is painted on the inside, plus there's other paint that's on the inside that's not painting the surface. The surface is paper thin. So we want to think about how we resolve Gabriel's paradox. Finite volume, infinite surface area. So think about that. Think about that for Thursday. We'll talk about on Thursday how you can resolve that paradox. Hopefully it won't give you a headache. All right, so let's do just a regular old one that doesn't take as much thinking. So we're going to take this curve and we're going to rotate it around the x-axis from 0 to infinity and figure out whether we have a finite volume or not. Finite volume or an infinite volume. So when you look at that curve, if I were to ask you whether the area beneath it from 0 to infinity were finite or infinite, what would you probably guess? Does it look like that curve approaches the x-axis fast? No way. But we just saw with Gabriel's horn that you can have a curve that does not approach the x-axis very fast, namely 1 over x, but we did get finite volume. Right? We did get finite volume, so it's possible to have a curve that has infinite area beneath it to rotate around and actually create something with finite volume. So go ahead and set this up and see what you get. So we're going to use the disk method, of course. So set this one up. So with the pi r squared, we're just squaring the function. And we have to put a pi out there, so we'll put the pi in front. Squaring this, when we square the numerator, we get just x. In the denominator, we have x squared plus 1 to the 2/3 when we square it. So that's what you should have gotten for your setup. You're just squaring the function. And we are going to turn this into a limit as b goes to infinity. 0 to b. Now, what technique of integration are we going to use?
Inverse tan?
Nope. Because there's the extra x in the numerator. So if there wasn't that extra x in the numerator, you still wouldn't have inverse tan immediately, but you could use trig sub. You could use the tangent function for trig sub. But the first technique we always think of if it doesn't have an immediate antiderivative is substitution. Substitution only works if whatever you're going to let u equal has a derivative that's around. Well, normally we let u be whatever's in parentheses, whatever's in the square root, whatever's in the exponent, whatever's in the angle. If we let u be that, its derivative is 2x, which is right there, or at least ish. Just have to multiply it by 2. So substitution is going to work. So we're going to let u equal x squared plus 1. So du will be 2x dx. And if we want to, we could isolate x dx since that's what we're seeing in the numerator. So this is going to give us pi limit integral. So we're letting u be down in the denominator, so it's going to be u to the negative 2/3 if we pop it up top. And then x times dx is du over 2, so we're going to put a du on the inside and we can put an over 2 on the outside. We can factor that constant out to the front. Du over 2. We don't want to deal with these limits shifting. It's a real pain when you shift the limits and then have to take the limit. It's a lot easier to go back, so you just have a b in the end that you can take the limit as b goes to infinity. It's easier. So then we can do our regular power rule business. We get u to the 1/3, divide by 1/3 is multiplied by 3. These are placeholder limits. This will be 3 pi halves, 3 pi over 2. Limit, back substitute, we said u is x squared plus 1. And when we back substitute, we get back to our original limits. So now we're back to 0 and b again. Back to x limits. Let's plug our limits in. We get 3 pi over 2. So then we're going to plug in the b. So limit, this will be as b goes to infinity. Plug in the b, we get b squared plus 1 raised to the 3rd power. Minus, plug in 0. 0 plus 1 is 1. Raised to the 1, well, I guess we're going to leave parentheses there. 1 to the 3rd power is 1. We get that. So, b is racing off towards infinity. If you square b and add 1, so inside here, that's still going to plus infinity. Take a number and square it and add 1. It's going to be going to infinity. What about then if you raise it to the 3rd power? What's it going to?
Still positive.
Still positive infinity, right? 1/3 power is a bird wing. Just like the square root of x, the 3rd root of x, the 4th root of x, the 5th root of x, x to the 2/9 power, any fractional exponent. Any exponent less than 1, you got the bird wing, it's going to infinity. Always. So that's still going to plus infinity. And if you subtract 1 from a quantity that's going to infinity, that quantity is still going to
Positive infinity.
positive infinity, still go in that direction. All right, so, and then if you multiply by 3 pi over 2, it's still going to plus infinity. All right, so this volume is in fact infinite. This volume is infinite. So infinite volume there. Lots of volume. Well, functions can be horizontally unbounded or vertically unbounded. Horizontally unbounded functions are obvious because you see infinity or negative infinity in your limits of integration. So they're obvious. This is something that they mention in Calc 1, but they don't really drive home. This integral right here is an improper integral. It looks deceptively like a definite integral. Like if you just write this down, integral a to b f of x dx, oh, it looks like a definite integral. But the one caveat in Calc 1 is that the function needs to be continuous on the interval ab. But 99% of the time in Calc 1, you didn't even think about whether the function was continuous or not on that interval, and you just integrated blindly. Now we need to be super careful. If we have a definite looking integral, we need to look deeper and make sure that the function is continuous on the interval. If you look at the graph of this function, it's not continuous on the interval. It's discontinuous at a. So it is an improper integral with a vertical tail. So this is unbounded in the vertical direction instead of unbounded in the horizontal direction. And we have 3 choices. It can be unbounded to the right of a vertical asymptote. It can be unbounded to the left of a vertical asymptote, or you could have this double problem. So these are vertically unbounded. And what we do for a vertically unbounded is choose a random c so that this is a definite integral. And then we're going to let c approach the asymptote. And this takes a one-sided limit. C has to approach a from the right. Right? You can't approach a from the left because that's not even part of the region. We have to stay within our region. So C has to go to A from the right. Down here, C would have to go to B from the left. And if we have the double problem, we split it at the asymptote and do 2 separate improper integrals. And then add them together. So let's try one of these unbounded vertical problems. So here is a picture of our 1 over x squared, which we already found the horizontal tail for. We already found that that gray tail had area 1. That was the very first problem we did today with this section. So we know the gray tail is 1 square unit. When we look at the blue tail, the vertical tail, does that look like the curve approaches the y-axis fast enough to have a finite area? No. That's looking infinite. And so we already did this horizontal tail here. We already know that this is equal to 1. If I'm remembering correctly from the first problem we did. I think that's what we got for our area. So we already know that. Let's check the vertical tail. So when you look at this, it looks just like a definite integral. But what we need to now, and it's not obvious, like the horizontal tail, you see infinity in the exponent, in the limit of integration. Here we don't see that it's improper, so we have to ask ourselves, is our function continuous on that interval? And the answer is obviously no, because if you plug in 0, you get undefined. This is not even defined at 0, so we can't integrate it with a regular definite integral. So what we have to do is break that apart. So we're going to turn it into a limit. And we're going to say C is going to go to A from the right of C to 1, x to the negative 2, dx. So we're coming up here, and our idea is that we're going to drop this vertical line right there. That's at a random x, but we're not going to call it x, actually. We're going to call this C. We're going to call that C. Why are you cannot now? Okay. And we're going to be approaching 0. Oh, when I said A, the problem actually gives us a lower limit. In the general description, they call that A. But we actually have a number now, so let's use that number. So we're going to approach 0 from the right. So we are going to find the definite integral that's going to find this area. That's going to be a function of C. And then we're going to take the limit as C goes to not infinity, but 0. So we have to be careful with that limit. It's not at infinity like the other one is. So let's go ahead and do the integral. So this becomes limit. Antiderivative here, minus 1 over x. Add 1 divided by the new exponent. Plug in our upper and lower limits. I guess we can come sideways, leave it all on the board. So we're going to have negative 1 plus 1 over c. And this limit is as c is going to go to 0 from the right. All right, so calculating this limit. Limit of negative 1 is a constant, it's itself. Limit of a constant is itself. The obvious problem is over here. So, it's not going to infinity though, right? We're letting c go to 0. So when we think about the denominator going to 0, that means the fraction values are getting bigger. As this goes to 0, you think about it being 1, fraction value of 1. You think about it going to 0.1, then your fraction value is 10. Then you think about it going to 0.001, your fraction value goes to 100. So this fraction right here is getting bigger as that c is getting closer to 0. So in your mind, when you have c going to 0, think 1, 1/10, 100th, 1,000th. And then when you flip that, you get 1, 10, 100, 1,000. So as c goes to 0, this piece right here, that is going to go towards positive infinity. And if you subtract 1 from that, you still have positive infinity.
Should it be minus 1 over c?
It's minus a minus, though. So when we plug in the upper limit, we get
gotcha.
negative 1.
Yep.
And then the fundamental theorem of calculus says subtract off what you get when you plug in the lower limit. So it's 1 minus 1 over c. See it?
Yeah.
And so what we are going to notice is this whack-a-mole type of thing. When we have these powers of x, if it's tight on x, it's going to be loose on y. And then on Thursday, we'll see that if it's tight on y, it's going to be loose on x. So we're always going to have this thing where one tail is infinite, one tail is finite, other than 1 over x. With 1 over x, it's going to be infinite on both tails. But for the most part, as this power on x changes, you're going to have the one side finite and one side infinite. All right, so let's stop there, and I will see you all Thursday. Good luck. Good luck out there. I will stick around as long as you need me. 2 hours and 15 minutes wasn't enough now. I can do more.
We've covered